Hello lovely viewers, welcome to my first video about programming for my Retro 6K fantasy computer entertainment system. We are going to, of course, tackle Hello World on practically bare metal because, to be honest, there aren't a whole lot of features in the firmware of this system yet. So we're pretty much going to do everything from scratch, and you know what? That's the way I like it. Or so I tell myself. Anywho, let's consult the programmer's guide. We want to go to, first thing we want to do is the cartridge container file format. Now we can actually trick our assembler into not only creating the necessary ROM image for the Retro 6K computer, but we can make it generate the file header as well. So let's get started with that. Here we go. Here's our hello world.6502 file. And the first thing we're going to do is we're going to tell our assembler do the following bytes, because as it says in the programming guide, we want 47, A9, 02, 6A, BB, 47, 3, finally A7. And so the dollar signs here are telling the assembler that these are hexadecimal numbers. Next thing that needs to come in the file, offset to the page flags array. We'll figure that out in a minute. 4-byte little Indian number. Well, let's just for the moment say just call it a bunch of zeros. We'll fix that in a minute. And another offset. Let's see. Duplicate this line. We'll fix these little things in a bit. And the extension data, we'll just use byte sequence of all zeros. This will stay all zeros. Now we need to do the page flags array. This cartridge, let's just do 1 kilobyte of RAM. 1 kilobyte of ROM, I mean. That means we've got 4 pages of read-only memory. So we'll do block of $01 for 4 bytes. Or does it go the other way around? Yep, I did that backwards. You want 4 bytes with value hexadecimal 01. And then the remainder, 156 bytes, of no memory chips installed whatsoever. That'll be 0, no memory at this address. Now, how do we get our offset to our page flags table? Well, let's start by inserting a label here, container start, and a label here, page flags start, and then we can have the assembler do the math for us and say page flag start minus container start, and we have to break this up into 2 bytes. Well, I mean, it'll probably only be 1 byte in reality, but let's just treat it as a 2-byte value. We'll do this symbol makes it insert the low byte of the expression, and then the high byte of the expression, and then zeros just to fill out the 32-bit number. This will almost never be more than a 16-bit number in this field, but just future-proofing the format, I define it as a 32-bit number. Same thing for the beginning of the ROM image. ROM image start, which has to begin at address 2000 hexadecimal, because that is the beginning of the cartridge memory space in the Retro 6K system. Now we can do the same thing here. ROM image start minus container start, except this .org makes it a separate segment, and the assembler only does things 1 segment at a time. So when it's generating this, it doesn't know where ROM image start is going to be, but we know where it's going to be. So we'll just say $2000 minus container start. And again, do the high byte. Now there's one last little hiccup, is that the assembler isn't going to know what address this container start label is going to be, or more likely it'll assume it starts at 0, so it'll allocate 8 kilobytes for this header, which is going to be, in reality, much less than that. But we can do .org 1F00. That'll give us plenty of room, 256 bytes for the container header before the ROM image starts. We can actually do less than that. I don't know off the top of my head how much space we actually need, so we'll just do 256 bytes, and that should start. And now we should have, when we generate this, when we assemble this, we should have a valid cartridge file defining a cartridge with 1 kilobyte of blank memory. So we'll save this file. We'll go to the command prompt here. am going to check. I actually have a batch file to take care of this to make it fairly easy, but I'll type it out here just to show this at the start. VASM 6502 old style win32.exe. That is the VASM assembler targeting the 6502 architecture with old style format, compiled to run for Windows. We will use the check labels flag, the escapes flag. I actually forget what this -x does. You can look it up in the VASM manual. Use a dot in front of directives. Optimize branch instructions. And now we do our source file name. And format binary. And output to helloworld.r6k cart. Oh, there we go. 180 bytes is actually how much room we need in the header. Not a whole 256. So, well, close enough. Let's fire up the Retro 6K emulator. Oh wait, first we need to move the file to where the emulator will look for it. Alright, now let's run our emulator. There we go, and that's not the right aspect ratio. So, it turns out, the last thing I did when I worked on the code for this emulator was I added the bit of code that actually reads the size and aspect ratio information from the configuration file. But I forgot to actually compile the release version, which is what I usually use when I want to test my cartridges. So I've done that now, and here we go. Let's load the Hello World cartridge and see what happens. System does not detect that the cartridge is even there, and I'll tell you why. It's because we didn't put the correct magic number in the cartridge ROM image. So let's take care of that. Here we go. Cartridge header. The first 10 bytes of the cartridge memory identifies the cartridge. So we'll just insert 10 bytes here. And if we use the .text directive instead of the .ascii directive, then it won't put a trailing null byte there, which is good because we need something following that to be something other than a null byte. We need the magic number. A7, A9, 0C, 1E. Next next thing we need is the program entry address. And we'll just put in a label here, which is not defined at the moment, but it will be in a minute. So next we want to do the interrupt handling code. At this point in development, the Retro 6K doesn't use interrupts at all, but that will change in the future. In the meantime, or well, future-proofing against that rather, so all the interrupt handler will do is say return from interrupt. Now we can put our label main entry, and here's where we can put our actual code. For the moment, let's just have it do nothing. Well, we'll have it do something. We'll have it do an infinite loop. Jump back to main entry. So it'll jump right back to the same jump instruction. And that is pretty much the tightest infinite loop you can have. Well, okay, it can be slightly tighter if you use a branch instruction instead of a jump instruction, because that'll generally read fewer bytes before it decides it needs to actually jump. But save this. I will use my batch file to run it, to assemble it and move it to where it needs to go. Actually, I'm going to use a different batch file. Hang on a second. Okay, so I have a new batch file that assembles the source and moves it to the correct place. Let's see, where's my window here? It basically calls two other batch files, which are this one, which either takes 2 or 3 arguments. It just calls the assembler. And install, which just moves the file. So, let's run that batch file now. AI hello world. So there it did the assembling, and it moved one file. Now let's run our emulator again. There we go. Now, instead of displaying the intro screen and saying, please insert a cartridge, instead, after simply verifying that a cartridge has been inserted, it jumps right into the cartridge code, which does nothing, so we get this screen of mostly uninitialized memory. So, technically these are characters on the screen here. The font has not been initialized. So let's write the code to do that. Alright, we are going to use a feature of the Retro 6K called Fast Video Memory Copy, because we can only write to video memory during the times when the video output is not actually outputting any proper pixels. That is during the horizontal retrace and vertical retrace periods. So we have a limited time with which we can do that, and when we need to copy the font from bank EROM into video memory, that takes a little bit of time to do. So this fast video memory copy makes it go a little bit faster. So what we need to do is comment here. We'll start by setting the fast video memory copy destination page. We want to write to page, we could do the entire font, but for this program all we need are the pages containing the characters hexadecimal 40 through 7F. We don't even need all those actually, but that'll be pages E4 through E7 in ROM and 1.4 through 1.7 in video memory. So we'll load 1.4 and write that to address 03F8. Then E4 is our source. Store that in 03F9. And now we just need a loop to do our copying. Now when we're using fast video memory copy, the CPU doesn't even realize that it's copying. It's just writing any random value at a particular address, and this fast video memory copy circuit actually changes that so that the video memory sees its address and data and write enable lines set to write, while the general memory, where the data is being read from, sees the address that it needs to read from, and its write enable is not enabled. So then the data just gets put on the bus by this memory and immediately read on the bus by this memory. And the CPU doesn't have to do a load and then a store. It just needs a single instruction to set that up for the memory to talk to each other. So what we can do is write store 00 indexed with the X register. But we need to do that 256 times with a different value of the X register for each time. So we'll initialize X register with 0. Do our copy that doesn't look like a copy. Increment X. And how do we know when we're done? Well, we're done when X loops around from FF back to 00, which will set the doing increment X resulting in X wrapping back around to 0 sets the 0 flag of the processor status register. So we can do branch if equal, or rather branch if the 0 flag is clear, to, now we need a label. Call it font copy 4, actually. I was going to call it 0, but 4. Now where does that label need to go? Well, it needs to go right here. So that will copy first half of the uppercase alphabet. Now we need to do this again with 3 more pages of data. So we'll do load page 1.5 from page E5, called loop font copy 5, branch to font copy 5, again 6, 6, 6, 6, and 7, 7, 7, 7. Now let's clear our FVMC registers by putting zeros back in them. Let's save this and see what happens. Assemble and install Hello World. And run the emulator. That doesn't look like it worked, did it? And I just realized we got rid of our do nothing loop. So we don't even know what it's trying to do. Just to satisfy our curiosity here, let's open up the debugging tools. See if we can figure out what it's doing. That's just a whole lot of garbage. In fact, program counter 1B, it's actually executing video memory as if it's code. If it's even successfully reading the video memory, it might be reading who knows what. Because if the video memory is in use by the actual video circuitry, then the CPU can't access it. So, there's a couple things we need to do here. First of all, let's put a halt loop here at the end. Label called halt. And have it simply jump to halt. But remember why we need the fast video memory copy in the first place? It's because we only have a limited amount of time where we can actually do the copy. So we need to wait for when that time actually is. So let's do that by checking part of memory. System status addresses. What we want is the video status. We need to figure out the horizontal scan state, the vertical scan state. Actually, all we really need to do is wait for vertical retrace. So we only need bits 4 and 5. And we want to look for a value of 2. That'd be bit 5 is set, bit 4 is clear. We don't care about what any of the other bits are. So, we will make a loop called wait vscan 4. We will load accumulator from register or from memory address 02FC, which is not real memory, but that will select the status lines coming from the video circuitry. And then do a bitwise AND with bits 4 and 5, which is hexadecimal 30. Compare that with the value we're looking for is vertical rescan starting, which is 2, but it's actually shifted over because it's in bits 4 and 5, not bits 0 and 1. So it'll be hexadecimal 20. And if the vertical rescan is indeed starting, then our 0 flag will now be set. Otherwise, it will be clear. So we want to do branch if not equal. In other words, if the 0 flag is clear, go back up to wait vscan 4. Save it, assemble it, and run it. That still doesn't look right. Is it maybe because none of the characters on the screen are in that range? I don't know. I'm going to, you know what? Let's insert actually a bit of debug break, which is described here. All we need to do is write a non-zero value to address 03FF. So let's load an FF and store it at 03FF. See what the emulator does with that. It's not even getting there. What's going on? Stuck in that loop. Oh, that's my bad. This is something that I mess up a lot when I'm writing 6502 assembly. Whenever I want to load a literal value, I need to remember to put a little hash sign in front of it. Otherwise, it'll try to load from that memory address. So this applies to our fast video memory copy setup as well. And our debug break. This is actually memory address 00, but really all that's doing is saying is the low bits of the address are all zeros, plus whatever is in X. That's all the fast video memory copy at work. Hash mark, hash mark, hash mark. Hash mark, hash mark, hash mark, hash mark, hash mark, hash mark. Hash mark. And you know what? If you saw that mistake before I did, good. Reward yourself with a cookie if you want. Or whatever other treat. Alright, let's save and assemble and run. Well, it hit our debug break. Still doesn't look like it's working right. Okay, another stupid mistake. I need this to say branch if not equal. Because if it's equal, then it's done. If it's not equal, we need to loop. Let's get rid of this bit of debug break there. Alright, now let's see if we got it this time. Well, I see parts of some letters. There's an H. Okie dokie. So, you know what's happening? It doesn't actually have time to copy all of the font data that it needs to do. We actually need to do our waiting loop before every page of font data. So we need to do it here, here, and here. And just change numbers in our labels. Of course, these labels can be anything, just as long as they're not the same for multiple different loops, because then you'd have duplicate labels. But I'm naming them 4 through 7 because of the memory addresses that each one deals with. It's just something I like to do. Let's see what we get now. Hey, it kinda works, and it even says hello world at the bottom. But why is that? We didn't program it to say hello world. Well, you know, we kinda sorta did, but actually what's really going on here is the firmware puts, before it sends execution to the code in the cartridge, it actually initializes a little bit of screen memory with the identification of the cartridge there in the bottom center of the screen. So that's what that is. Now, it still looks kind of glitchy because we never initialized other characters that are used for surrounding that space. But that's okay, for now we don't need those. Well, maybe we do. Probably at least want the blank space to work, so we want to do pages, or we want to do page 1, 2 loaded from ROM page E2 as well. So we'll just copy this. E2, E2, wait scan 2, wait scan 2, font copy 2, font copy 2. See what we get now. I am aware that this video is not going quickly. And you know what? I am not exactly an experienced YouTuber, but I hope you'll bear with me. And for some people who are new at this, maybe going slow is better. And at the same time, there's some things that I'm doing and not really explaining very well. So, sorry about that. Alright, well, we've got space characters to the left and right of the cartridge identification. But what we actually want to do on our Hello World program is have it actually write Hello World on the screen, not have the firmware do it for us, just by way of having the cartridge header include that text. So, let's get down to business. font data. Let's write some text. So, this will be pretty straightforward. Load A, letter H, store A, address 0800. That is the location for the upper left character cell on the screen. Let's continue doing this. And we want to do a comment only. And looks like we didn't quite need this last one. I copied and pasted just a bit too many times. So we don't need to write all these at 0800. We want to do them in 801, 802, 803, and so on. Let's take a look at our results. There is a slightly more elegant way to do this, which I think I'll get to in future videos, because this is already dragging on kind of long. I think I already decided I would do improvements to the Hello World program in subsequent videos, so this pretty much just makes that crystal clear that that's what I'm going to do. Okay, command prompt. AI Hello World. Run the emulator. And what do we have? Something doesn't look right. That looks like the top of an E, bottom of an L, top of an L, and then some garbage. Well, guess what? It ran out of time. We need to put in another wait loop. We could also put this wait loop in a subroutine. I'll save that for a future video. But something else was up with that. I don't know if you caught it, but only half of the letters were showing up. Let's take another look at that. There's an R. I'll tell you what's wrong here. Parts of video memory that define what colors to use have not been initialized. Yeah. That's a bit of a problem, isn't it? So, let's take care of that. It really is doing it from scratch, isn't it? Of course, we could re-engineer the firmware. I mean, I, as a designer of the computer, could re-engineer the firmware to handle some of this initialization. But I am of the opinion that games and software may not want to wait for the firmware to do some initializations that it's just going to overwrite with its own choices anyway. That could be a fraction of a second wasted in load time. So, let's check the programming guide here. We want to look at, I'm going to go memory layout, video memory. Okay. Video memory at addresses A800 to, or 0800 to 083F. Take switch characters. We've already done that. Now I want to do the color assignments. This is going to be a little bit trickier because for each character, we need to write to 5 different locations in memory. So, what we want to do is make sure that the first 14 cells of text have primary and secondary foreground colors are one thing, and primary and secondary background colors are another. Let's just do color 1 for foreground and color 0 for background. So, we can do let's see, the low nibble of the byte that we want will refer to the even-numbered row of text, which is what we want. The high nibble will be for the following row of text. Since we don't really care, we'll just do the same nibble twice. And we're going to set the bits for bit 0 of the color data, which will be 1 for the foreground and 0 for the background. Okay, referring to the section on the stock character set, the font that we're loading from ROM, that is the ROM that's built into the system, not the ROM in our cartridge, defines these the per cell colors as going primary background, secondary background, primary foreground, secondary foreground. Now we want to set bit 0 of the color selection in our cells to be clear for the backgrounds and set for the foregrounds. And these are bits 0, 1, 2, and 3 of the nibble. So we want 0 and 1 clear, 2 and 3 set. That is a hexadecimal C. So for both rows of text, we want that arrangement of bits. So we'll do load hexadecimal CC into the accumulator, and then store that at memory location 0A40. That refers to the upper left cell, plane 0. That is bit 0 of the color selections. I am sorry for beginners at how complicated this part is. I'm gonna come up with some shortcuts later. But here we go. 0A40 plus 120 times plane 0, so that's 0. Row is 0, so all that does 0. So our byte address is 0A40. Also a column there. Column is 0, but we want to do this for other columns too. So 0A41. I want to go all the way up to column 0C, so 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Let's do a comment here so we can kind of tell what we're doing when we look at the code again. Now we want to do $0, because the other 4 bits of the color selection for all 4 colors of the cells will just be 0. So we need to do this again, but 4 more times, incrementing the address by 0120 hexadecimal each time. So A40 becomes B60. And then C8. Autocomplete in Notepad++ is kind of annoying. And DA. It occurs to me that the autocomplete menu isn't even showing up on the video, because that's technically a second window, so you can't see how it's getting in my way. Finally, for bit 4, I'm going to do this in the range EC0 through ECC. Alright, let's save, let's assemble, and let's run. See what we get. It's all black. To make sure the cartridge identification is legible at the bottom of the screen while the cartridge is loading the font or loading whatever else it wants to do, it actually does set the palette entries. And it sets most of them to black, so we need to change palette entry 1 to something else. Load A EC and store A at address 0FE 1. That is the address for pallet entry number 1 out of 32. Save, and assemble, and run. Hey, it's orange. That is not the color I thought it would be. Oh well, at least we can read it. One thing to note though, that's not a comma. That's a Roman numeral 12. What went wrong there? I'll tell you what went wrong. Retro 6K doesn't use ASCII by default. So when we tell the assembler to load A with a comma, the assembler uses the ASCII code for comma, which is not what we want in the Retro 6K. That would be character 2C, which in the Retro 6K stock character set is this Roman numeral. So where did the comma go? The comma in the stock character set is at character point 3C. So instead of saying it's a comma, we want to say load hexadecimal 3C. And I think we have the same problem with the exclamation mark too, now that I think about it. Exclamation point is at 1-1 instead of 2-1. So that means we need to load more font because we don't have pages 1 and 3 of the font. So, where's the exclamation mark? Alright, so it turns out I forgot to close the emulator after the previous run, so when I was doing that code editing just now, you didn't see it. You just saw the version of the emulator that wasn't quite working right. So here's the version of the cartridge that copies 7 pages of font. And here's where I said, where's the exclamation point? So let me pause recording to investigate that. Okay, so I found the problem. Here where I changed a bunch of B6s to C8s, this one should have stayed a B6. For bit 1 of the color assignments, we want to do 0B60 through 0B6C, and then bit 2 we go 0C80 through 0C8C. And so 0C8C was premature here, and it never got to do 0B6C. Also, the color bit, EB is the shade of green that I want, not EC. So we'll save. We will assemble and run. I inserted a debug break in there too. There we go. But that garbage on the line below is kind of distracting. Since we're setting the color of those cells at the same time as we're setting the color of the cells we actually want to change, we can fix that pretty easily. So here's where we do setting bit 0. We have it clear, or set for the foregrounds, clear for the backgrounds, but we want to do even row only, and that's the low nibble. We'll just set the high nibble here to 0. You know what, while we're at it, let's make the primary and secondary foreground colors different. So let's let's do color 1 for the primary foreground and color 2 for the secondary foreground. We do that by doing only the primary foreground on bit 0, so we get an 8. And then for bit 1, let's see, bit 0 set only for primary foreground, even row only. Here we do set bit 1 to be set for secondary foreground of even row only. Oh, my mistake. Primary foreground is going to be a 4. Secondary foreground is going to be the 8. And then after we've set our bit 1s for various cells, all other color bits clear. So here we set our palette entry 1. What would make a good color for palette entry 2? How about a darker green? Load hexadecimal 92. Store it at... Don't use hash signs in store instructions. That just doesn't work. 0 FP2. Save and assemble and run. Oh, I forgot to take out the debug break again. There we go, two-tone text. Let me just take out that debug break. There we go. Save, assemble, run. I think I'm going to call this good enough for our first attempt at a hello world. In the next video, how about we clean up the rest of this garbage, then maybe do some fancy things, like I'm thinking maybe have the message hello world bounce around the screen like a DVD player screensaver. What do you think about that? Anyway, thank you for watching. This has been a longer video than I thought it would be. Probably less exciting than I thought it would be, but you know what? If you're really into this, I bet you stuck around through the whole thing. And if you did, I really appreciate it. So thanks again for watching my first programming for the Retro 6K video. Like and subscribe, I guess, particularly if you want to see more of these. I hope I will make them a little tighter in the future. It's going to be my bedtime soon. Good night, everyone.